Okay, so what do we know here? So we're trying to figure out how long it takes the elevator to reach a speed of 4 meters per second. Well, that sounds like kinematic stuff. So ultimately, we've got to turn this into some kind of a kinematics equation, right? Kinematics problem. So what is all this nonsense at the start about forces how's that gonna help us turn this into a kinematics problem? Okay.
Define average velocity.
Okay, well, maybe, that's a way we could maybe do this. When we're talking about forces, force is fundamentally linked to what kinematic quantity? Well, just think in general, Newton's second law, what's that tell us? Force equals what? MA. F equals MA, right? So force is related to acceleration, isn't it? Right? Okay, so in other words, if we see an acceleration occurring, we know there has to be some net force acting on the object, right? Okay. All right, so talk to me about this then. So we know when the elevator is at rest, the person standing on a scale gets a reading of 760 newtons. Okay, what's a newton? It's just a unit of force, isn't it? Now, we're not used to that unit. We use, whenever we talk about forces, almost always, what unit do we use? In the US? Pounds. Yeah, that's really a dumb one. Pounds, like most of our units, pounds make no sense. Newtons make sense. How come? Because newtons are the units that are naturally built from the MKS units that we use in favor in physics, right? We like to use kilograms, meters, and seconds to build everything. Well, what do you suppose? Oops, frozen. What do you suppose 1 Newton equals in terms of kilograms, meters, and seconds, given that Newton's second law just tells us that net force equals mass times acceleration? What do you think the units are that make up a Newton?
1 gram, 9.8. That's the acceleration value.
Okay, so you're looking at this and you're saying units of mass and units of acceleration. What's our standard unit of mass? No, kilogram, right? We use MKS, meters, kilograms, seconds. So it's going to be 1 kilogram times meters per second squared. Yeah, so it's a kilogram meter per second squared is what a Newton really breaks down to, if you think about it in terms of just its base units. But that's kind of inconvenient to always write it that way. So, and we use force a lot in physics, so we just give it its own name and call it a Newton. Okay? All right, so if the scale reads 760 newtons when the elevator's at rest, something changes when the when the elevator begins moving upward. So what's it doing? It was at rest and it starts moving upward, it must be accelerating. It's accelerating upward. Now the scale reads 820 newtons. Okay, so talk to me about that a little bit. Is that scale measuring weight? What does the scale really measure? Okay, well that's weight. That's weight, right? That's a person's weight. Yeah, so think about a scale. Now, if I'm standing on a scale, gravity's pushing me down, right? Well, what's pushing me up? The scale is, right? The scale is between me and the floor, and so the scale is what's pushing me upward, right? So what do you think a scale is? How do you think it's made? Well, it's just kind of like this, right? There's typically like in an old-fashioned scale at least, there's a spring in there, right? There's a spring in there, and when the scale pushes up on you, it compresses that spring, right? And so when it compresses the spring, that turns a dial and it reads out whatever it's depending how accurate it is, it reads out the weight, the pushing force that it's applying to you, right? The normal force that's supporting you. Now, like in the first example up here, if the elevator's at rest, if we were to draw a free body diagram, and let's do that, wouldn't the free body diagram just look like that? Right? What are the two forces that are acting on the object, the scale? Okay, so gravity's pushing down, right? And what is a person's weight? It's the force of gravity, but how do we calculate that? So we know Newton's law tells us that F equals ma, but specifically, what is the acceleration acting on us when we're talking about weight? Gravity, right? So it's just mg, right? That is weight. That's what the force of gravity is weight, right? What is g, by the way? We should probably write that down. G is our pseudo constant. What is it roughly near the surface of the Earth? Yeah, 9.80 meters per second squared down, right? So that's one force. What's the upward force? Yeah, the scale, we might call it normal force, right? It's the surface of the scale is pushing up on us. And so we could call that normal force. Okay, when the elevator is at rest, what can you tell me about those two forces? They have to cancel each other out, don't they? Because what's the net force? Zero, because I'm not accelerating, right? So they must be equal in magnitude, right? Now, if we wanted to think about this in terms of what we're going to come to call an equation of motion, we're going to break up the, in the near future, we're going to take complicated systems of forces acting on an object, and we're going to orthogonalize them, which is really a nasty sounding word, but that all that means is break them up into components, which we're good at. We've already done that, right? We're going to break them up into, say, horizontal and vertical components, and then we'll just, we'll look at how the vertical forces all balance, all the components, and how the horizontal forces all balance. Well, this is an easy example here. We're not there yet, so don't panic. I'm just throwing out there where we're going to go. But this is pretty simple because there's only two forces and they're both acting vertically, right? So couldn't we say then that the net force, which is all in the y direction here, well, what is it? If we add up those forces, there are two of them, right? We've got the normal force, which is positive because it's acting in the positive direction. And then we've got the force of gravity, which is what sign? Negative because it's pointing down, right? So we get F sub n plus mg, which is negative. So I'm going to make that a minus sign, right? And what is the net force you told me? Zero, right? So there's the equation of motion that we get that comes from that free body diagram, right? All we did was just added up those two forces. One's positive, one's negative. And we know that the acceleration is zero, so they add to zero, right? They're in equilibrium vertically when the elevator's at rest. Okay, so what is the scale measuring then? Well, normal force, if I just add mg to the other side, I get normal force just equals my weight. Ta-da, right? So the scale did measure my weight there, didn't it? Indirectly, right? It really measured the normal force, which was equal to my weight when the scale was at rest. Okay, does that make sense? Now, look at the second part of this, though. Second part of this, when the elevator starts to accelerate upward, the scale reading increased. Now, did my weight change? No, my weight's my weight, right? So the weight is still mg, but this time, the normal force must have been a little bit bigger. Right? So in addition to supporting my weight, it was also providing an additional force that was accelerating me upward, right? So there is a little bit left over. There's a net force there, right? So I could resolve this down to the case where there is a positive net force acting upward, right? Make sense? Okay, so you can tell me what that force is. What is the net force? How'd you get 60? You're right.
220 minus 22.
Yeah, because I know from part A that my weight is 760, isn't it? Right? So if there's 820 newtons of force now pushing upward, that means there's 60 left over, right? There's a net force of 60 vertically, isn't there? Right? So then we know here, if we go to this other page over here, we know that if we look at this equation of motion, the normal force minus mg is equal to ma, right? There actually is it's not zero this time. We know that there is a net force, so I do have some acceleration. Net force is just, Newton's first law tells us, it's just ma, right? Mass times acceleration. Well, we can calculate the acceleration this time, can't we? Right? We almost have everything we need. What is the normal force that's acting? When we're moving upward? 820. Okay, so this is 820 minus mg is 760, isn't it? If I just knew my mass, I could solve that, couldn't I? Right? Right? Can I find my mass? I can. Right there, can't I? Right? Because in part A, we'll call it, when the elevator was at rest, what was my normal force? 760, right? So up here, we know that 760 newtons equals m times g, but what's g? Right? So we can solve for m, can't we? Right? If I just divide both sides by 9.80 meters per second squared, we get the value for m, don't we? So what is that? What is that? What do we get from that? So this tells us that m equals what? Somebody with a calculator. 77.35? 55. Okay, so I'll just call it 77, roughly 77.6, and you'll just store that in your calculator, right? Okay, so it's that many kilograms, isn't it? Because remember what a Newton was? A kilogram meter per second squared divided by a meter per second squared. The meter per second squareds cancel, and we just get kilograms. Do we even need to worry about it though? No, that's why we use newtons, because newtons play nicely with meters and seconds, right? We could even just forget about the units. They're going to work out if we use newtons, right? So that's our mass. Right? Now we can solve for acceleration. Okay, so we get the equation 820 minus 760 is just 60, right? So 60 newtons, which are kilogram meters per second squared, equals 77.6 kilograms times A. So we'll just divide both sides by 77.6 kilograms. So we get A, the kilograms cancel, and we get units of meters per second squared like we knew we would, right? And what do we get?
0.77.
Okay, so we get A is roughly 0.77 meters per second squared. But of course, you'll just keep that on your calculator, right? You'll keep it out there to spectacular numbers of sig figs. And now this just devolves into a kinematics problem. Now it's boring, right? I mean, we've done all the, we took advantage of the free body diagrams and our understanding of the forces to calculate an acceleration, and now we just want to know how long it takes to go from, what was it, rest to 4 meters per second with that acceleration, right? So we could just go to another page and write down our kinematic stuff. What's our initial velocity? 0, because it started at rest, right? Our final velocity, did we say it was 4? Let's make it 4.0, so we add another sig fig. The acceleration was roughly 0.77 meters per second squared, but we've got it stored. And then we're just trying to find T, right? So what's the kinematics equation that relates those quantities? Second one, yeah. V final equals, and we usually don't put the final, what would we called it a 1, didn't we? In the book, they use V1 instead of V final, same thing. Plus AT, and what's V naught? So we can just get rid of that. So what's the only thing we have to do to solve for T?
Divide B by A.
Yeah, just divide both sides by A, right? So we end up with T equals V final, so that's 4.0 meters per second divided by A, which is roughly 0.77 meters per second. And what do we get to two places if we do that?
5.17.
5.17, so roughly 5.2 seconds. That's how long it takes. Pretty cool. We can do that. Does that make you feel smart? Physics is, I just love physics. Physics is the ultimate way to train, to just strengthen your brain. It's all it is problem solving. Even more so than math. I mean, math gets kind of prescriptive in a way. You've got to, you got certain, but physics, there's just always so much going on that you have to build these models and use the models, and it's the, I just like it so much better than playing math. Okay, so what I want to do for today, that was a good example, but I want to just plug in a tiny little piece, and then I'm going to put some problem sets up. Yesterday I had a little spare time yesterday, so I built a bunch of Moodle problems to go with this section. And so I'm going to, rather than doing a bunch of problems out of the book, most of these, this unit we can do on Moodle. So I'll put those on there and assign problem sets based on, probably distinguished by math just a little bit, but not much, won't be too much of a difference. I want to push through one more little section though today. We'll talk about friction. Really interesting. So and when I say friction here, I'm specifically referring to surface friction. Because there are other types of friction too, right? We could have, for example, fluid friction. If you dive into a swimming pool, you slow down pretty quickly, don't you? Right, because of the fluid friction. Put your hand out the window of a car, and you can feel it going fast. You can definitely feel the air resistance, fluid friction. But we're talking about surface friction here, right? Okay, surface friction is what occurs when two different objects rub past one another, right? So do this real quick. What do you feel? It gets warm from the friction, right? Different surfaces have differing amounts of friction between them. Some surfaces are very slippery and have low friction. Some surfaces are rough and they have high friction. So what causes it? What causes this friction? Well, it's at a microscopic level, this is sort of what a surface looks like. Even a really smooth surface, like the smoothest surface you could get, highly polished metal, extremely smooth. I mean, that's what we make mirrors from, right? It's polished silver, so it's really, really, really super shiny and smooth. If you look microscopically, you think it looks absolutely smooth? No, it doesn't. It's still bumpy. Even those highly polished surfaces, if you look at a microscopic level, they look like this, right? And so we've got this top surface and this bottom surface, and based on that understanding of what the microscopic structure is, what do you think causes the friction? Yeah, to be really technical, it's the little bumpies. When they run into each other, that causes friction, right? That provides a stopping force. So why would one surface be slipperier than another surface? Yeah, sort of the nature of the bumpies. How many of them there are and how tall they are, right? How deep the valleys are and how tall the peaks are. If it's got bigger bumpies and more of them, then you're going to see that's going to cause more friction, right? there's another thing, and it's a little more complicated than just that. There are some other things going on too. Sometimes the bumpies are flexible, and so when the bumpies are flexible, they'll kind of just move past each other and then wobble back into place when the surfaces slide past one another. So that makes it slipperier, right? So there are a few other things that contribute to this. The elasticity of the surface, if it's able to kind of be a little bit flexible and displace as it moves past each other, okay, slipperier.
What about ice?
Okay, what about ice though? Ice is different. Ice really is different. Ice is, glad you brought that up, it's an interesting topic. Ice is not inherently slippery. Now, I'll prove it. If you get really cold ice and you take it out of the freezer, does it slip real easily on your hand? It doesn't, right? It almost sticks a little bit, doesn't it? Yeah. And there's some other stuff going on there too. It's cheating a little bit, but ice is not inherently slippery. What makes ice so slippery is this very peculiar quality that water has, which is unlike, I don't know if there's any other substance that does this, but this is really unique to water, and like so many things on our planet, it just is, we could literally talk all period just about ice. There's so much good stuff to talk about with ice. Its unique properties make Earth suitable for life. I mean, if ice weren't the way it was, there wouldn't be life, at least big life like us on Earth. But for today, I'll keep myself in check and I'll resist that strong temptation to just talk about that all period. Ice, unlike other materials, when you apply pressure, high pressure to ice, it turns liquid. The solid becomes liquid. That's not what happens with other materials. And so the reason that, for example, an ice skate slips on ice, but I mean, I can't even, it just makes my skin crawl thinking about the sound an ice skate would make if you tried to skate on like metal or something. Ugh. Right? I mean, it wouldn't work at all. It'd be very high friction, right? Ice is different though, because with ice, think what an ice skate looks like. It's literally just a blade that you're standing on, right? Well, what is that doing? I'm going to show you. We haven't talked about this yet, but it's coming up. I mean, pressure is defined as force divided by area, right? So if an elephant steps on your feet, it's not going to be as bad as you think, because the elephant has kind of soft feet, and they're really big. Elephants have large feet, and so the area of contact with the ground is so big that the pressure is not very high, right? Because you get, a lot of force, but it's also divided by a big surface area, and so the pressure is not very big. You'd be much worse off if a woman in, what are those really pointy heels called?
High heels.
Stiletto, yeah. Seriously, you'd be much worse off if a woman in high heels stepped on you like that with just a heel. The pressure would be much higher than an elephant, because even though the force would be not nearly as high, the surface area is tiny. And so that means you're dividing, the denominator is really small in this fraction. Small denominator equals big fraction, right? So the pressure is really high. Does that make sense? We'll talk more about that later. But with an ice skate, if you look at what an ice skate is, if we were to look right along the blade, it just looks like this, right? It comes down to this relatively sharp corner. And so there's a very small piece of the metal that's actually in contact with the ice. Well, even a person's, not huge weight, a person doesn't weigh a ton compared to other things, but a person pushing down on that ice skate creates really high pressure. And so it creates this little bead of water along the bottom of the ice skate, because the pressure liquefies the ice, right? And so what are you really doing? You're not gliding on the ice. It's cheating. You're gliding on the water that coats the ice. And so there's a lubricant there. The ice is sticky, but the water that coats it makes it slippery. Good question. But that's different, right? It's still, all the stuff that we're going to talk about can apply to ice, but that's why it's so slippery. Okay, so we got our model, right? We got our surface model of why there's friction. The little bumpies are rubbing past one another. When we talk about surface friction, we really have to divide the friction up into two different categories, though. We have to think about surfaces that are moving past one another, that are actively sliding, and then surfaces that are at rest relative to one another. Okay, which one do you think experiences stronger friction? Just thinking about our model. What do you think? It's actually static. Actually static. And the main reason why is a little bit tricky, but one reason that's a little bit easier to see, if I let these surfaces, given that the surfaces are a little bit flexible, if I let them come to rest, they'll kind of press into each other, right? And the peaks will kind of slide by each other, and so they'll sort of embed each other. The peaks, does that make sense? But another thing that happens that's kind of cheating is, at a microscopic level, what makes up a surface? Any surface. What's all this stuff made of? Well, okay, yeah, but if you subdivide it, I think I heard it. Matter, which is made of atoms. Yeah, what are atoms made of? Atoms are made of charged particles. And so when the little atoms in the little pointies get really close to each other, like right here, you can actually experience an electromagnetic force is created where the surfaces are drawn together. And so it literally creates little microscopic welds in the materials where they kind of are pushed together. Now, when the surfaces slide past one another, they never have an opportunity to do that because they're always kind of bouncing by each other. But when you let them sit, they develop these little micro welds, which are then have to be broken when you push the thing and make the surfaces slide. So static friction is always stronger, static meaning at rest, than kinetic friction. Kinetic means movement, right? So then kinetic friction. The model that we use to describe friction is about the same mathematically for both. And I really want to emphasize that this is a model. Everything we do in physics, as amazing and fascinating as it is, and it allows us to describe the world, you always have to keep in mind that we're just using models to make predictions. How good are the models? Well, sometimes really good, but not perfect. So this mathematical model that I'm going to show you is not perfect. It's just pretty good. Just a pretty good way to describe friction. This is how you do it. For static friction, the frictional force is equal to mu sub s times normal force. Now what is that? Mu sub s. Mu is a funky looking Greek letter, and it's called the coefficient of friction. So in this equation, it's the coefficient of static friction.
Isn't that also used for like micro?
Yeah, it is. It's used for different contexts. It's used for different things. But when you're talking about friction, it's understood that it stands for the coefficient of friction. So there it's used to represent the coefficient of static friction. For kinetic friction, the equation looks the same. The frictional force equals mu sub k times normal force. What do you suppose that stands for?
Coefficient of
That's it. Coefficient of kinetic friction. Okay, so what does that mean? Well, first of all, a coefficient, we know what coefficients are, right? Coefficients in math are just numbers that are multiplied by variables, right? Similar here. A coefficient is a unitless quantity, so it doesn't have any units associated with it, that's multiplied by a quantity that has units, right? So, and how do we get them? You measure them. The coefficient of static friction for, say, what are we going to do for rubber on smooth concrete? That is a number that people have measured in a laboratory and publish in a list. That's all it is, seriously. So you could go online and you could Google coefficients of friction and you'd get this big long list of all these different materials and what the coefficients of friction are between those materials. If you want to be really precise about it, it's going to even vary depending on, temperature and things like that. Like when rubber gets heated up, it's stickier than when it's colder, right? So we're not going to probably be that precise about it. So these coefficients, what you'll always find though, is for any pair of surfaces, the static coefficient is always going to be greater than the kinetic coefficient. Okay? That's important and it's useful. if you're gonna go buy a car to go to college, even if it's a used car to go to college, your parents probably want you to have a safe car, right? So what kind of braking system would you really like to have on your college car? Automatic? What's the, yeah, true. That'd be nice. But when you, even if you just have the kind where you step on the brake, what's the preferred kind of braking?
You mean like how
I
just
think
like,
it's right.
it doesn't like go.
Okay, well, sure, but that's the mechanism, but, I mean, you're familiar with anti-lock brakes, right?
Yeah.
Okay, anti-lock brakes are huge. Anti-lock brakes, they dramatically reduce your stopping distance. How do they work?
They
You know?
like, instead of like stopping all at once, it kind of like goes moving ways.
Say it again?
Instead of
Yeah.
stopping, it keeps it going, so which isn't as much.
Yeah, think when you're gonna stop in a hurry, if you don't have anti-lock brakes and you jam on the brakes, what happens?
You like it, the brakes on, we still like skid.
You skid, don't you? Yeah, you skid. So the rubber is actually being dragged across the concrete.
Like it
Is that
stops, but your car doesn't like actually stop.
right? Okay, until eventually it comes to rest,
Yeah.
right? But while it's moving, while the car is still moving, the surfaces are sliding by each other, aren't they? And so what kind of friction is that? Kinetic or static? Kinetic, because the surfaces are moving, right? Okay, now, what would you rather do? Well, people that are highly trained drivers, even if they don't have anti-lock brakes, even if you know something about physics, you'll always probably do this now. If you do what's called threshold braking, where you're gonna push down pretty hard, but if it starts to lock up, you ease up a little bit. So you're using the maximum braking force that you can without actually initiating a skid. Then is the tire actually moving relative to the road? Because it's rolling, isn't it? When a tire rolls, what do you know? I've even got a tire here to demonstrate this. When a tire rolls, is it static or kinetic friction? It's static, because the actual part of the rubber that's in contact with the road is not sliding, right? So what do anti-lock brakes do? Well, anti-lock brakes, the way they accomplish this is they take advantage of the flexibility of rubber, and they just modulate the pressure in the brake fluid many, many times a second. Like I think it's typically something like 10 to 20 times a second. They're going to turn the brakes on and off. So they turn the brakes on. When they clamp the brakes down, what happens? Well, the rubber it comes to rest, and it starts to skid a little bit, but it stretches, and so it never actually slides, and then it lets go, and the rubber reforms again. It springs back, and then it starts to skid again, and so the rubber gets stretched. And so effectively what happens is it's the equivalent of threshold braking, where you're never quite skidding, but you're almost skidding. So you're taking advantage of the higher coefficient of static friction to give you more braking force. Very clever, right? So that's how it works. By the same token, if you have some of these new fancy cars, if they have what's called like traction control, right? Or like Subarus have this. So if you want to be able to, it's really important on the ice too. The anti-lock brakes are huge on the ice because there is a really big difference between kinetic and static friction on the ice. I mean, it's like more than twice as strong. The static frictional force is more than twice as strong than the kinetic frictional force. So your stopping distance is substantially impacted. But even if you want to take off, in a car, if you want to take off and you push down on the gas.
Good afternoon, Buckaroos. It's Charlie here for your Charlie Cat time in the afternoon because we have a Friday assembly tomorrow, the Native American Assembly. Here's your Camp Food Drive announcements. In the semifinals for the annual Camp Food Drive is Mrs. Bixler versus Mrs. Emmerich and Mrs. Stewart versus Mrs. Kelm. The total cans brought for so far are 1,325 cans from PHS alone. Remember, if you lost, you're still in the Challenger round, and congrats to Mrs. Flaggart for winning the Challenger round. Make sure that